Now let's consider this reaction where you have sodium thiosulfate, which is reacted with hydrochloric acid. So when acid is added to the sodium thiosulfate, we just start the timer and we're going to monitor the time that it takes for the X mark on the paper. So this is an X that has been drawn, and we're going to record the time that it takes for that X mark to disappear. Why? Because as the reaction takes place, you have a precipitate which is formed. So the speed at which the precipitate forms indicates the rate of the reaction. So let's watch a video that shows this reaction.
For getting down to eye level so I can see the level of the sodium thiosulfate. I fill up my measuring cylinder. Ooh, almost there, little bit more, until I've got exactly 50 centimetres cubed measured out, and I'm going to pour that into the beaker. I'm now going to measure out just 10 of the acid, so I'm using a slightly smaller measuring cylinder. And again, getting down to eye level, holding the measuring cylinder firmly so it doesn't fall over, and measuring out exactly 10 centimetres cubed. You can use a dropping pipette to do that, but I don't. Now, the reaction is going to start as soon as I mix the acid with my sodium thiosulfate. So I need to be ready with my timer to start as soon as I add it. Just a swirl or two to get them well mixed, and then I'm going to observe the cross through the solution by looking directly above. Now, after a few seconds, you start to see the precipitate forming and the solution turning this cloudy yellow colour. But I'm going to watch from above until the cross has totally disappeared. Now, and stop the timer. And so I've got a time for my first concentration of 27.44 seconds.
Now, this experiment can be carried out at different temperatures. So if we increase the temperature, normally the rate of the reaction is going to increase. So sketch the graph of time taken for solution to go cloudy against temperature. So we'll have time taken is first, so this goes on y-axis. So time, let's say per minute, and temperature is going to be per degrees Celsius. So as temperature increases, the reaction is going to become faster. So if reaction, so rate increases when temperature increases, therefore time taken for the reaction to occur is going to decrease. Right? So because the reaction is going to become faster. So with increasing temperature, time taken is going to decrease. It's not going to reach 0. So here is the 0 mark. It's not going to reach 0 because anyway the reaction is going to take time to occur. So it's going to decrease like this. Sketch the graph of rate against time for the reaction at room temperature and then at 60 degrees on the same axis. Label the two lines. So we'll have a graph of rate against time. So as the reaction takes place, the rate of the reaction is going to decrease. Now, if we're considering the same temperature as the reaction occurs, the rate is going to decrease. If you still remember what we did last week, so as the reaction proceeds, the speed is going to slow down until the reaction stops, until all the reagents are used up. Then the reaction is going to stop. When the reaction stops, rate is 0. So rate is going to decrease until it reaches 0. So here we have a decreasing rate. Now this is at room temperature. Now if we carry out the reaction at a higher temperature, the initial rate is going to be higher because when temperature is higher, rate is going to be higher. So initial rate will be higher. but the reaction is going to be faster, which means that it's going to take less time to be completed. So if the reaction took, let's say, initially took 10 minutes to be over, if you carry it out at a higher temperature, it will be over within maybe 3-4 minutes. So rate is higher, but it will end, the reaction is going to end in less time. So in red you have 60 degrees Celsius. Okay. Now you have a fill in the blanks, so you can complete the fill in the blanks.